Okay, so I'm going to talk a little bit about Predbat internals and specifically today the actual planning code. So this is the portion of the code where, based on the current circumstances, Predbat builds a plan and then displays it to the user. So it's all in plan.py now, and there's this function called calculate plan. If it's called with recompute on, then essentially it's going to force a recompute. And if not, then it's going to decide whether it needs to recompute or not. So essentially the logic here is this sort of update the plan every 10 minutes or when something really important changes. So if one thing it has to do here is if it starts a new day that the hours wrap around, it has to recompute because all the minutes in Predbat are based on starting from midnight, so the plans become invalid as soon as you wrap over. Um, then it does some things here to just go, well, okay, if the current charge window is just ended, then move on to the next one, or if the current export window is just ended, move on to the next one. And then if we actually need to recompute the plan, then it will run the recomputing. So the first thing you need to do is essentially get the initial possible charge windows, which is called low rates here. So these are the potential charge windows. This is a calculating charge. If you're not, then we just take whatever the inverter's got set. And similar for export, we get the high export rate windows. So these will be taken from the threshold. So usually low rates is everything except the highest at the highest rate, which wouldn't be counted as a charge rate, except if you only got one rate and then it's just your import rate. And the high rates would essentially be everything except the lowest export rate in most cases. And so it sets up some empty charge limits based on that and some export limits. So this is all turned off to start with. And so this is just where it prints out what you start with before the optimization. Cloud coverage factor is essentially it works out the difference between the 50% and 90% PV scenarios. And sorry, the 10% and the 50% scenarios. And based on that, it's going to say approximately how much cloud coverage you might have. It's just an estimate, and it works out this cloud coverage figure, which we use later. Load divergence essentially works out the difference between your average load and your peak load within a certain period and works out a load divergence. And then from that, what we do is we take the predicted data for load, which could either come from the historical data that Predbat's gathered, or it could come from PredAI if you're using it. And then we apply the in-day adjustment, which was calculated earlier, any load scaling. And we also apply this cloud factor, which is essentially based on the load divergence in this case. So actually cloud factor just means it was because it was originally a cloud model, but now it was applied to load as well, and it essentially means the difference. So what happens is that your load will go up and down. So you turn the kettle on, it spikes for a bit, and then it goes off again. We just count a rough average, then you'll be able to say something like, oh, well, your PV is covering everything, so I don't need the battery anymore. But actually, when you turn the kettle on, you do need it. And so this attempts to model the spikiness of your load by the divergence between the average and the maximum. It essentially applies an adjustment to the load patterns. So it goes, and it does it in alternate 5 minutes. So it goes up and down, and it creates this spiky nature, which essentially prevents some of the bad assumptions from being made during the modeling. The difference between load minutes and load minutes 10 is the 10 is the pessimistic version that uses the higher load scaling 10 that the user might have set. And it also applies a higher load divergence factor. So this is kind of what I'm seeing in the worst case scenario factor. And these load minute steps and load minute step 10s are essentially just the actual every 5 minutes load numbers that we're going to apply during the modeling phase. And so this is much more optimized than the input data. Then does something similar for the PV forecast, except this time it's using the cloud coverage metric rather than the load divergence. And again, it does something more pessimistic on the cloud coverage for the 10% scenario than it does for the 50%. So you've now got kind of realistic and pessimistic curves, and those are ready for the predictions. This function here just calls something that calculates your yesterday's savings. It's just been called here whenever the plan's being updated. Then we do a single prediction here. So we essentially run a model. We create the prediction model, which we're going to use in a minute. We also create thread pools. So if you're multi-threading, it's going to create a pool of your CPU count or the number of threads you specified. Then we run a single prediction here with the current. So this is based on essentially how the base model looks. So this is before we've made adjustments to the plan. And then we run some calculations on the plan. So essentially, if we're recomputing the plan, then we run this optimize all windows, which is the thing that actually does all the plan optimization, comes up with the best plan. If you've got the tweak plan option enabled, then it will call that one as well. I'm not sure anyone uses that nowadays. Tweak plan is just something that optimizes the next few windows in detail. So the idea was that you'd be able to use it even if you weren't recomputing, but I'm not sure it's used much anymore. Remove intersecting windows, essentially, if you've got an export slot that clashes with a charge slot, it essentially removes that charge portion, potentially splitting it into multiple charge windows that are shorter, because if the export intersects it, because the actual execution plan needs just either an export, a charge, or nothing. It can't have them intersecting. Then discard unused export slots, essentially just gets rid of the ones we're not using. So it cleans up from a list of all the potentials to just the ones we selected. And then we run a prediction here based on the new plan that we've got, and we use that for clipping. So clipping is basically just trying to remove redundant instructions. So, for example, if I say it says export down to 90% battery, but you've only got 80% battery to start with, then it's redundant and it gets rid of these. So again, it cleans up the mess in your plan. So that's the clipping. And then clipping can also make unused slots that get removed. Then similar for the charging side, we then run another prediction based on where we're currently at. And we use that to essentially, we discard any unused charge slots, ones that aren't turned on, and we clip one. So if you say charge to 20% and your battery never gets down as low as 20%, it does nothing. And so we throw that one away. And then we run a final simulation of what they call base, which is the kind of with Predbat not doing anything, and then best, which is the new calculated plan. The save essentially saves this updates the Home Assistant entities with all the data. This is just a bit of rounding before we publish the data, and then we create the HTML plan also, which you can use, and we update. And if the web interface needs the history updating, it does that. And then if we've got a multi-threaded pool, we destroy it. So essentially that's the loop every time we update the plan. But this thing called optimize all windows is essentially the thing that does all the work. And if we drill a bit into optimize all windows, it's split into a few phases. So essentially it sorts all of the import and export slots by price. So you're essentially getting them in price order from the most expensive to the cheapest, and those are used later. And then we use this region calculation. So essentially the idea here is we're going to set a price level where below that level we're charging and above that level we're exporting. And so optimized charge limit price threads essentially is it's a multi-threaded, multi-processing pool version of that, where it tries to work out, it moves that price limit down and then picks the best one. But it also has to experiment with different export slots, because obviously, you could say, well, I can only import at 10 pence and that's good for my plan. But if your export price was 20p, then maybe you want to import up to 15 pence and you can still make a profit and export more. So it actually has to try the export slots to set that price threshold. Then it does the same thing, but it does it in little regions. So it starts breaking it down. So initially we start with if you've got, say, a 24-hour plan, then it splits into two 12-hour sections, and it actually recalculates the levels on those two 12-hour sections, and then it goes down into 6-hour sections and then 3-hour sections, for example. Actually, it's wrong. I start at 16 hours and go down to 4 hours. And so it repeats the leveling process, because actually the price levels can change over time. You might be willing to pay a higher price now because that's all you've got, but then later on in the future, the prices might be dropping and the level might move. So we come out of this process actually setting our price level. And then after that, we then do the second level of optimization. So we take the charge slots from the first one, we actually throw away the export slots because they'll get recalculated individually. And we essentially do this second thing where we go through three passes. First, we look at freeze slots, then we look at normal, and then we look at low. And the price values get reversed depending on which one we're doing. So freeze is only for export freeze, essentially, which is when we're exporting solar. So essentially we want the highest price ones first. So this is a charge slot here, so that it wouldn't be used for the freeze pass. It would only be using the export slots. And essentially, based on the price, we look at all the windows that hit that price threshold, and we essentially try and optimize whether it's a charge or an export window. We try and actually pick the best level to charge to or export to, or don't pick it at all. So it goes around this optimization loop here, doing this optimized charge limit for charge slots, or optimize export limit for export slots, essentially. So it calls it for all the different windows in all the different price bands, moving through the price bands, essentially from the most expensive to the cheapest. And I think the low is essentially where you when you start at the lowest price, move up, and that's essentially for picking extra charge slots that are above the price threshold, which you might need just for extra export slots. Where normal is essentially the charge slots below the price threshold, or the export slots above the price threshold, and freeze is essentially the export freeze, where you'd be above the price threshold. And so it goes around this loop, doing all these predictions and optimizations. And then when that finishes, depending on what settings you have, you're either done, or it does this calculate second pass if that's turned on. And that now goes, calculate second pass does the same thing, but it goes through in time order from the most recent slot to the furthest in time away slot, and it tries to optimize that way. This can produce some more accurate results in some cases, but it can also do things like bring export sooner when you decide you want it later in the day. So it doesn't necessarily do what you want depending on your planning, and it is also a bit slower because it does all the windows. And so that's how the optimization works. Then if we were to filter in on optimized charge limit only, then optimized charge limit is essentially a routine that tries to figure out the charge limit for a particular window. Or it can be a group of windows for the first level in the past, but let's just assume it's for one window for now. So essentially it works out which different values we're going to try. Now, for the moment, for only 30-minute slots, we either try charge on or off, or charge freeze if you want it enabled. For larger slots, so like an overnight window, we actually try different SOC values to charge to. And we essentially queue up all these different predictions with the different SOC values into a list, and then we schedule them on threads, and each of the threads runs in parallel. But we need some initial ones to work out the min and max SOC so we can optimize away. So, for example, if the charge level only got down to 50%, there'd be no point in trying charge levels below that, but we need to figure out where it would get to first. And so we can work out all the different charge levels that's worth trying, whether we're trying charge freeze or not. And then we can schedule all of those into the threads. And then we can collect back all the results. And then we can work out the one that's got the best metric by this computed metric. And the metric's quite complicated. It's not just price, it's a combination of all different factors into the metric, and it depends on how the users had it configured. And essentially, there's a couple of weightings which are little tiny tweaks to the metric, so that if you've got things of the same metric, it picks one or the other. So essentially, we try and weight towards not charging, or if you do charge, weighting towards 100% charge or charge freeze. Let's try and not have too much fluctuation in the values. And essentially, we're picking the best one. And then when they're all done, it kind of essentially returns the best one here. Optimize export is essentially the same thing, but it's doing it for export rather than charging. So you could do export off and export freeze, or you could do export down to 0. It doesn't try different export amounts, but it does try different lengths of export windows. And so essentially it's going to try different 5-minute intervals starting from the minimum size, which is 5 minutes, and up to the maximum size, which is the length of the window. So essentially we try all these different export options, and we pick the best one again based on the metric that's being selected. So the other thing to look at right now, if we're getting into too much depth, is the compute metric. So the compute metric essentially takes a whole bunch of things. So it takes the final state of the charge of your battery, and it works out a value on that state of charge. And it's doing this both for the 10% scenario and the 50% predictions. So because otherwise, one plan you might have 100% battery left, and it might cost you £1, and you might have another plan where you've got no battery left and it costs you 99p. Well, actually, the £1 one's a better deal, so you have to value in the battery on that one. Works how much iBoost you manage to deliver, which has also got some value. And it also works out the other things you can set, like metric battery cycle, which is basically how much did you use your battery. It counts in there. Counts in the carbon weighting if you decide to optimize for carbon. And it also counts in how much you imported, essentially, if you're counting self-sufficiency, and works out a final metric. So all of these things are taken into account in that metric calculation. So that gives you an idea of the sort of things that go into the optimizations. It's actually quite complicated. And of course, you have a read through the code yourself and see if you can figure it out. But it's just too much to go into every single detail there. So I just wanted to show you how this works out in practice. So this is a plan from Agile, which I ran. So it's an Agile import with a fixed rate export. So let's talk about the leveling process. So this is the output from the leveling process for the plan. So essentially it's picked some charge slots below a certain threshold. So You can ignore the colors here because the colors are only selected later on in the plan based on the thresholds. But here, essentially, it's decided to charge the 18.3p, 18.59, etc. And it's got some more charges down here. So this is basically the slots it thinks are worth charging on based on this plan. You can see we're staying above empty the entire time in this plan. So that's what the leveling ends up producing. Then the raw plan, so this is what we get out of optimize all windows. So after you done the leveling, and then the second pass of the plan where you actually go through the different price orders and select things. So this is the raw plan. So here we've got something fairly similar, but you can see it's added some other things to the plan that doesn't happen on the levels. So it's got some freeze charges in here. So freeze charge at 29%, so essentially holding the battery before charging. Because these slots are slightly more expensive, but if you count inverter losses, they're probably actually worth holding on. Hasn't added any export in this case. We don't have any export in this plan because the price of the import's higher. So unless we've got lots of spare solar, which we don't in this case, it's not worth it. Then the final plan is just this plan again, but with the clipping. And so what you'll see there is these freeze charge 29s are being combined into single slots. I don't know if anything's actually been removed. It looks like probably not. Let's just combine them. Actually, you saw on the raw, you didn't need any charging later on because of these freeze charging earlier. Those in the original plan levels, we had some charging on Sunday, but I think those Sundays, actually the Sunday's gone away now. The reason it's gone away is because it's so many hours after the first charge, the plan tends to end. So anyway, so that's the different phases. The other thing that's worth mentioning, so I generated this by replaying somebody else's plan. What you can do now, if you go to the Predbat web interface, you can actually download things for debug. So these are designed for filing a GitHub ticket. So you can download your apps.yaml. Obviously, you've got that in the file there anyway. You can download the Predbat log and the HTML plan. You can also download the Predbat debug YAML. You click on this, it does take a few seconds to actually generate it because it's quite a lot of data. But if you attach these 4 files to a GitHub ticket, then there's something quite useful here. The debug YAML gives me enough to actually reproduce anybody's plan, and I can play around with the settings and actually look at those different phases as well. You might just click keep because it's insecure, because it's the YAML file. But essentially, I can load that YAML file up and view it. But I can also load it into Predbat directly, and actually we can see. So if I switch across to the YAML file now, you can see so this gives me all my config items here. So if I search for something like export on charge, for example, I can see that value was set to false. So this has got all the data in. It's also got all of this step data in that I was talking about, all the different things about your predictions, etc. And so essentially, I can take one of these debug files and I can just run it through Predbat standalone and actually generate those HTML plans, and I can also change the settings and replay it. And so it's quite useful for debugging particular issues. So yeah, I think that's mostly what I wanted to show today. And then I suppose the other thing is then if you go back and you actually go into GitHub, yeah, and oh, not there, yeah. Then you can go to issues and then you can do new issue and can file a report, and then it actually asks you to attach the log file and this YAML file here. And so you can actually go and attach them. And you don't necessarily need the apps.yaml in a lot of cases because that's actually captured in the final output debug YAML. In some cases it's useful if you're debugging that specifically. But okay, well, I hope that's useful, and Thanks for watching. Bye for now.